And welcome everyone to session 2 of what we're calling practical astronomy. I really should call it observational astronomy. That's really what it is focused on. That's the intent of the course, is to help guide people through learning and advancing in techniques for observing the sky yourself. This is not a theoretical astronomy class. It is observational. Okay, and I will go ahead and start. If I can find share screen here. Yeah, see, he's still got September up there. Once again, tonight, we're going to be going over sky coordinates, and that's really the basis for understanding where things are in the sky and how to look them up. Without understanding sky coordinates, you're really going to be limited to things that you can see and learn on your own with very little additional information. And the second half of the session will be on telescope and mount designs. So we did a little bit of that last week, but today we'll go a little further in depth. And then next week, observing progression, how to kind of build on success, starting with things that are easy and moving to things that are harder, and how to know what things are easy or hard. Let me get some housekeeping things over here. And Jared, if you could monitor the chat, if anyone has any questions, go ahead and submit those in the chat tool, and Jared will curate them and interrupt me when appropriate. And I'll stop from time to time and ask if there are any questions. So finding objects is really perhaps the hardest part of amateur astronomy. Now, you can get a lot of help from modern computerized telescope mounts, but they're really no substitute for actually knowing the sky yourself. I kind of equate it to going into a new city and using GPS. And GPS is great, it'll help you out, but it's hard to know one thing relative to another or in relation to another unless you really learn the city yourself by living there. This is the best way. And living under the sky, which you do all the time, you can learn it as well as any city. I mentioned this last week. Most people think, if they think about it at all, that it takes a year or so to see the entirety of the celestial sphere, but that's not true. You can actually see all but a very narrow wedge of the sky if you stay up all night. Now, I know this is not something that you're going to all rush out and do, but I do recommend that perhaps 1 or 2 nights a year, you take the time to do this very thing. It really makes the sky look much smaller and more knowable than going out every few weeks and looking to see what's up right now. Learning the patterns of stars in the night skies, it's very rewarding on its own. I just enjoy looking, and some people have a real knack for it. Others, like me, struggle for years. And honestly, if I were to have to write down the Zodiac in order, I would probably fail that test. In the end, it's just a map, just like any other map, map of a city or map of the world. And here's how we do it. So I will say there was a good reason for the Ptolemaic system that I mentioned last year. It lasted for 1,200 years, perhaps really longer than that, but before the Copernican revolution. But the basic concept that the stars are stuck to a sphere and the Earth is at the center of that sphere is a useful concept. And that is the form of map that we use to this day. We know that the axis of the Earth is tilted 23.5 degrees relative to the plane of our orbit around the sun. And if we take the equator and project that line out into the heavens, we form a plane. And if we project that onto the celestial sphere, it forms a great circle called the celestial equator. But the sun, moon, and planets all move around this other line or this other plane. That great circle is called the ecliptic, and it's tilted 23.5 degrees from the celestial equator. Now, because it's tilted, because our axis is tilted, and these two planes are not parallel, they intersect at 2 points. And the 2 points they intersect at are called the vernal and autumnal equinoxes. And you're all familiar with that. You know that the end of summer just occurred at the autumnal equinox, and that winter will start at the winter solstice, and spring will start at the vernal equinox. Vernal literally means spring in Latin. Now on the sphere, we use a coordinate system, and there are 2 ordinates, and the names are kind of weird. The names of the ordinates are right ascension and declination. Right ascension is measured from the vernal equinox, and you see the symbol here is for Aries, because Aries is where the celestial coordinate system, well, that is where the vernal equinox existed when the coordinate system was established. In reality, the vernal equinox has moved, and I believe it's in Pisces. Doug, you may recall. And if you think, for example, that your sun sign, that you were born, for example, in May, you're a Taurus. Well, actually, you're an Aries. Yeah.
Is this the current vernal equinox? This point here?
Well,
that next to the gamma?
Yeah, well, this is the symbol for Aries.
Yeah, and then this would be the symbol for Pisces, since Pisces is right next to Aries.
Yeah.
If you had the symbol for it.
Right. Yeah, the point is the Earth's axis actually wobbles, which is called precession, and it takes 24,000 years. So 2,000 years ago, we're 1/12 of the way through the precessional circle, and 1/12 is exactly a month. So we're actually a month behind where the coordinate system was established. But that's sort of beside the point. I probably shouldn't have brought that up. But okay, so right ascension is measured in time units, hours, minutes, and seconds, but it is considered an angle. And 1 hour, and that angle is related to the Earth's motion 24 hours. So it's 360 degrees divided by 24, or 15 degrees. Now that's true only on the ecliptic, that it's actually 15 degrees, because up here, of course, at the celestial pole, it's 0 degrees, but it's just a matter of the cosine of your of your declination of your height here, how many degrees it actually is. But it's convenient for you to think of it as 15 degrees per hour. And another way to think of it is that 1 degree equals 4 minutes of time. This is not minutes of arc. I know this is a little bit confusing, but you have to think of right ascension in terms of time, not degrees, minutes, and seconds of arc. And then we have declination. And declination, so right ascension is this dimension, kind of equivalent to your longitude, really. And then declination is equivalent to your latitude, is the up and down motion. And its name makes a little more sense, how much of a decline or ascent you have. Now it is measured in degrees, minutes, and seconds of arc. So those declination units are always the same, as opposed to the time units translating. The time units translate to degrees differently depending on the declination, but you really don't need to know that. I mean, you don't need to use that. It's immaterial, really. So the key is that right ascension is measured in time units. Declination is measured in traditional angle units of degrees, minutes, and seconds of arc. So for example, here is the coordinate for this star right here. It is 1 hour and 34 minutes and 20 seconds RA, and then declination is plus 47 degrees, 36 minutes and 14 seconds. Now, when you're standing on the Earth, you can't see the entire celestial sphere. You have a horizon. And there are some key things that are local to wherever you are on Earth. It's just part of your local coordinate system, if you will. So the Earth behaves like a giant clock. We know that we complete one circle every 24 hours. Now, technically, there is a difference between solar time and what is called sidereal time, and that difference is 4 minutes, because it takes a little bit longer. The Earth in one day has moved slightly around the sun, 1/365th of its journey around the sun. So in order to come back and look directly back at the sun, where the sun will be exactly overhead once again, we have to go a little bit further than if we turn around and look at a specific star. So a solar day is 4 minutes longer than a sidereal day, but you don't really need to know that. They're close enough to where you just think about it as 24 hours. So right ascension, it's a funny name, and it gets its name from the fact that if you face north, then everything that comes into view, the sun, the moon, the stars, everything rises in the east, which is to your right. So things ascend on the right as you're facing north. So the hour angle that is at your local meridian, and the meridian is the line that connects north to south, projected up into the celestial sphere. So in other words, it's the line that goes straight overhead. That is called your local meridian. And the hour angle that is at your local meridian at any given moment is the local sidereal time, or star time. Sidereal is Greek, I believe, for star. It may be Latin, I don't know. And the angle from the north horizon to Polaris, we're kind of lucky because it just so happens that Polaris happens to be at very close to the North Pole, North Celestial Pole. And that angle is your latitude, and that becomes important later on when we talk about telescope mounts. So here is an image. It's kind of a pictorial image of the entire sky. This is very much, in fact, I think it is a Mercator projection of the sky. And because it's a Mercator projection, the further north or further south you get, the more distorted the images are. So for example, here's the Big Dipper, which looks nothing like this, of course. It's just stretched too far at the north. But at the equatorial region, things look rather normal.
Jeff, that was
Yes.
the Little Dipper, and over here's the Big Dipper.
Oh, you're right. That's Ursa Minor.
And they both look skewed.
Yeah. Here's the Big Dipper. It looks okay, not too bad. Yeah, this is Ursa Minor, the Little Dipper. The Little Bear, too. Okay, so we've got our celestial equator runs right down the middle, actually connecting this point to this point to this point. And then this yellow-green line is the ecliptic. That's the line that the sun and all the planets go through. And you can see the zodiac here. I'm just looking, Aries. Aries is not, oh, here's Aries. So the vernal equinox originally was at Aries, but now is in Pisces. And then here's Taurus, Gemini, Cancer, Leo, Virgo, Libra, Sagittarius, oh, Scorpius, Sagittarius, Capricorn, Aquarius. This is a more common way to look at the type of map, and they are very often portrayed in kind of negative, you know, with a white background and black or other color stars and objects. This happens to be a map of all the Messier objects. Now, this thing that's swooping through here, and it was, I believe, yeah, swooping through here as well. This is the Milky Way. So you see that it's the Milky Way, and this is the ecliptic. This map actually didn't have the ecliptic in it, so I drew it in myself, which is why it's not perfectly sinusoidal. Now, we're all familiar with constellations, but constellations in astronomy mean something a little bit different than you may be accustomed to. Normally, you think of a constellation as a grouping of stars, but as astronomers, when we refer to a constellation, we are really referring to a specific area of the sky. It is really a complicated shape within which are the stars that typically make up the constellation. And the IAU, the International Astronomical Union, is the governing body charged with naming and mapping the sky and everything in it. They're the same group that demoted Pluto from a planet to a dwarf planet. I happen to think they were right. Even as a young person, I thought, you know, Pluto's a weirdo. Sometimes its orbit is closer to the sun than Neptune. It's not a well-behaved planet. Its orbit is tilted more than any other planet. Why did they ever let it into the club? So the IAU has partitioned the entire sky into 88 constellations. Now that's for both Northern Hemisphere and Southern Hemisphere. We typically don't need to learn the southern ones, but you're welcome to learn them all if you want. And any point in the sky, RA and DEC, if you call out any coordinate, then that point is in one and only one specific constellation. So mathematically, the sky is a partitioning of the constellations make up a complete partitioning of the sky. And consequently, once the IAU did this, and I should have found out exactly when that was, when they standardized the map. Some of the ancient constellations are no longer recognized. And in fact, we've got, well, I'll show you in a moment. I'm actually going to skip this. I had some trouble with this, and it wasn't very effective anyway, but it kind of shows some common constellations and then takes you around based on their distances. Constellations may look like a dipper, but when you spin them around or travel around them, they're going to look differently. So here's really a map of the partitioning without the stars. And a couple of things you see, we've got the Zodiac highlighted with bold outline. And one thing that you may notice is there are, I think this is the only one. Serpens is the serpent is divided into two regions, Serpens cauda and Serpens caput. Serpens cauda is the head of the serpent and the tail. And frankly, I'm not sure I'm pointing to the head here. I don't know if the head's here or there. I forget which one's which.
This one's the head and this one's the tail.
Well, which one am I on right now?
The head.
Okay. I always forget which one's which.
Yeah, it can be confusing.
And technically, Ophiuchus should be one of the members of the Zodiac because the sun goes through Ophiuchus just a little bit. I think it actually grazes the corner like right around here. But that's another thing. Then we've also got, in ancient times, there was the Argo, the ship that Jason sailed in. It is now divided into three constellations. Puppis, which is like the poop deck. Vela is the sail, right? Mm-hmm. And Carina is that's the body of the ship?
Yeah, the hull of the ship.
The hull, right, the hull. Thank you.
Hey, Jeff.
Now, yeah.
I was going to say the IAU, they formalized the constellations in 1928 and then published it in 1930. So since 1930,
okay,
there have been 88 constellations.
Yeah, thanks for looking that up.
Mm-hmm.
I'll add that into the slide. In observational astronomy, asterisms are often more useful to us than constellations. Because there are no boundaries in the sky, it's hard to know whether you're in one constellation or another unless you look it up on a map. And it's really the maps that matter when you're dealing with one constellation or another. But asterisms are popularly known patterns or groups of stars that can be seen. And it may appear quite similar to the definition of constellation, but now that you know constellations are really a partitioning of the sky, asterisms are groupings of stars. So it's more of a visually obvious collection, and then the imaginary lines used to mentally connect them. There are no official asterisms. I don't think the IAU addresses them at all. But we know quite a number of them. For example, the Big Dipper is not a constellation, it's an asterism. It is a portion, really only about 1/3 of Ursa Major, the Big Bear. And Cassiopeia, we're familiar with the W of Cassiopeia more than any of the other stars that are part of Cassiopeia. And here's a few more fairly well-known, or one very important asterism, I should say, the Summer Triangle. And it's quite prominent right now. And so I really wanted to feature it. And it is comprised of Vega, which is the brightest star you'll see overhead in the summer. And that's part of the constellation Lyra. And then Deneb, which is the tail of Cygnus. And Altair, that forms the Summer Triangle. This is very large. So it's quite a large triangle, but it is rather prominent. Now, one of the key things kind of within the Summer Triangle is if you look along the line between Vega and Altair, about 40% of the way from Altair is this thing called the coat hanger. And I didn't want to include the technical name for it here. We'll just call it the coat hanger for now, and we'll get into its catalog number later. But it's a wonderful target for binoculars. You can make it out with the naked eye, but it's a little faint, but not, you can find it. It's findable. Here's a couple more. The teapot of Sagittarius. Honestly, I simply equate the teapot with Sagittarius. As far as I'm concerned, that is Sagittarius. Likewise, the Great Square of Pegasus. It's called the Great Square because it is truly large. And Pegasus is one of the largest constellations, if not the largest. I frankly don't know if it is or not.
Jeff, a lot of asterisms are kind of colloquial. They're
correct. Yeah.
They're various. Nations have their own.
Right, different cultures and
different cultures. Like the Big Dipper here in North America, and in like British countries, English, Great Britain, Scotland, and all that, they call it the plow.
Yeah, that's right.
And the Scorpius, the Hawaiians traditionally call it the fishhook.
Yeah, in South America, Orion is called the alligator or caiman because Orion is flipped upside down. Its feet are up by its head and the head down by its feet.
Okay, so enough about the equatorial coordinate system. I'm sure you've got it all down by now. So now we're going to flip to another coordinate system, a local coordinate system called the altitude azimuth or ALTAZ system. So it's really often convenient to orient yourself to your local position on the Earth relative to the sky. And your local coordinates are often used for your telescope orientation. Now, it's not really important that you ever be able to manually transform between ALTAZ and equatorial coordinates. You can use software to do that typically. I've never really had the need to do that. But many telescopes are built on mounts that use ALTAZ or ALTAZ kind of orientations. And this is what it looks like. Now, I referred to your meridian earlier, and your meridian is the circle, really a line, but it looks like the line that goes from due south straight overhead to due north. And straight ahead, straight above you is your zenith. Actually, there's a word for straight below you. It's called nadir, N-A-D-I-R, nadir. But you can't see it, so it's of no use. But your zenith is often useful. And then, of course, your horizon is like this, whereas the Earth's equator projected into the sky, or the celestial equator, is this blue line. Now, the coordinates, when you're referring to something in Altaz coordinate system, your azimuth, or your left-right orientation, is 0 at north, and then you sweep around clockwise from that to form an angle. And both ordinates in the Altaz coordinate system are angles, like you're familiar with: degrees, minutes, and seconds. The advantage of Altaz coordinate system really is that it is always local to the observer. So no matter where you are, that Altaz coordinate system is relative to you, not relative to the Earth or anything else. And it coincides with the most common type of telescope mount, which is also called Altaz. Now, even when using an equatorial, or perhaps especially when using an equatorial mount, there's often a big difference between looking east and looking west. And that is based on your local meridian. Now, you're not going to find any maps written in Altaz coordinates, because since the Altaz coordinate system is relative to the observer, the map would change everywhere you moved. Not by moving around in a circle or something like that, standing in one spot on the Earth, but as you move from one spot to another on the Earth, and time gets into it as well. And if you really need to transform one to the other, it's easy enough to use software. But like I said, I really have never had to do that. It's more a coordinate system of convenience than it is a coordinate system that you need to know anything about, number-wise. Okay, another important thing that people are always curious about, in fact, I would say this is probably the #1 question you'll get anytime you share a view through your telescope, and that is, how far away is the object you're looking at? And over time, you will find that you don't personally care that much about how far something away is, because you get kind of numb to the distances. The distances are so phenomenal. But people will ask you, and distances are important in astronomy. It's one of the most important things astronomers try to determine, really. But the objects are usually measured in one of 3 distances. So you're probably most familiar with light time, light years, but it could be light minutes or light hours. This is most commonly used by non-professionals for long distances, for great distances. Now, the speed of light is 30,000 kilometers per second, and that is an easy number to remember. If you try to remember it in miles per second, it's a little bit harder, 186,000. But this number becomes very convenient in a lot of situations. So 1 light year, or the distance that light travels in 1 year, it's just too big to even fathom. 9 times 10 to the 12 kilometers, or 6 times 10 to the 12 miles. That's 6 trillion miles. But here's a nice little trivia, and you can remember this. Light travels about 1 foot in 1 nanosecond. And that's because a foot is about 0.3 meters. And if you divide 3,000,000 meters, 3,000,000 meters is 300 million meters by a billion. If you divide 300 million by a billion, you get 0.3, which is about 1 foot. So there's a little trivia that you can keep around and use at your next dinner party. Now, the second type of distance unit is the parsec. And really that is the most commonly used distance for professionals dealing with stellar distances. And it's about 31 trillion kilometers. It's about 3¼ light years. And that's how I always remember the relationship really is 3¼ light years, or roughly, let's see, I can go if I go 3 times that, I'll get 10. So 10 light years is roughly 3 parsecs. Is another way to remember it. And then the third type of unit is the astronomical unit, which is the distance from the Earth to the sun. Now, 1 AU is pretty big. It's 93 million miles. But in terms of dealing with stars and nebula and galaxies, it's puny. It's way too small. So these units, astronomical units, are only good within the solar system. So the distance to the nearest star is about 4¼ light years. I'm not going to get into a fight over which star is the nearest, but let's just assume it's 4¼ light years away, and that's about 270,000 astronomical units. So even the closest star is over 250,000 astronomical units away. So every other star is typically millions of astronomical units. And here's what a parsec is. So how did they come up with the parsec? It's the distance from the sun at which the radius of the Earth, the radius of Earth's orbit, subtends an angle of 1 second of arc. So a star put out way out here has to be far enough away that this angle is 1/3600th of a degree. And it comes out to, like I said, about 3¼ light years. I do have a movie that I think is very good, and I will show that. And I think I set everything up. Give me a thumbs up if you can hear the sound.